This video is sponsored by Skillshare. The furnace in Minecraft is pretty special. It's one of the first things you need in the game, and this coal-burning cube can accomplish many simple tasks. After all, heat is useful. But if all it ever did was cook food and melt stuff, I don't think it would have captured my imagination with the same intensity that it did when I first realized you could power a minecart with it. Now, my real-life minecart videos should be a pretty clear indication of just how much I love the minecart, which is why building a furnace cart has been my obsession ever since. But before I build that, I need a furnace, and not just a hot stone oven. This furnace needs to take the energy of burning coal and somehow use it to steadily move the minecart across the tracks. This design is another big step in that direction, an experimental prototype powered by technology that's used by NASA. Now, it's not the only way to build a Minecraft furnace, but I think you'll find it just might be one of the coolest. So here's how I did it. As you might guess, building the original minecart was a lot of work, but the powerful electric motor was able to propel it up to the maximum in-game minecart diagonal speed of just over 25 miles per hour. A truly thrilling experience. So it seemed a shame to have to hack it to pieces. Either that or build an entirely new one. Let me explain. The most obvious choice for a coal-powered rail car is of course a steam engine, which is why I dedicated an entire video to building a prototype and exploring this as an option for a furnace cart. But hooking it up to the drivetrain of my current minecart would likely require a substantial amount of modification, or require me to build an entirely new minecart around the furnace. And would the motor be inside of the furnace, or just the boiler? Would the furnace have a rotating shaft sticking out of it? Where exactly do the two meet? Plus, a boiler system was just plain intimidating. The more comments I read, the more I realized just how dangerous they can be when improperly designed or operated. I was starting to consider other options, particularly because a steam engine needs water, but the furnace cart doesn't. Many comments suggested Stirling engines, which are basically steam engines without the water, but without digging into the complexity of those, I quickly began to gravitate towards a third option based on the following logic. What if I was able to create a furnace that takes coal and turns it into electricity? And what if it was able to do this without any big or complicated moving parts? By making it into an electric generator, not only could it be used to power a variety of different items in my base, but I could also connect it to the existing minecart drivetrain with minimal modification. But how do you convert heat into electricity with minimal moving parts? Well, it turns out that all you need are some very expensive squares. Now this is the NASA part, but the technology is actually pretty simple. Imagine that this thermoelectric cell is a tiny windmill. Without the motion of the wind passing through the blades, it wouldn't be able to spin and generate electricity, and it's the same with heat and this cell. It's not enough to just get one side of the cell hot. We have to dissipate that heat from the other side as quickly as possible. In effect, we're passing the heat through the cell, kinda like the wind is passing through a windmill, and we do that by sucking the heat away with giant heat sinks. The core of my design is a 12-inch aluminum cube, and this is where the coal burns, and it's also where we're gonna get our heat from. Our heat windmills, or TEG cells, will be mounted to either side of the furnace, but not directly. We have to make a special sandwich of specific materials in order to create the ideal thermal transfer from the cube wall to the heatsink. And the two main ingredients are anodized plates and thermal grease. The anodized plates electrically insulate the TEG cells because otherwise they'll short circuit on the raw aluminum. And the thermal grease fills the tiny gaps in the imperfect surfaces and helps ensure that the heat will flow evenly between them. So basically, we have heatsink, then grease, then anodized plate, then grease, then cells, then grease, then anodized plate, then more grease, then furnace wall, then support braces, then titanium screws, which are expensive but necessary. Titanium can handle a lot of heat, but it does not transfer that heat very well. We want the heat to pass through the hot furnace to the cold heat sinks, but only through the TEG cells, not through the screws. Simple, right? Looking at this heater core, it's crazy to think that there was a time when I couldn't even take apart a VCR without breaking it. New skills are always available to those with a little time and determination. And thankfully, there's an easier way to acquire them with today's sponsor, Skillshare. Skillshare is an online learning community with thousands of classes to choose from. Now, I've always struggled with choosing fonts for my YouTube thumbnails. It was so bad that I couldn't even articulate what I liked about the fonts that I liked. But the class Typography That Works by Ellen Lupton was a revelation. In just over 30 minutes of lessons, I finally felt that I had a set of concrete tools for better thumbnail composition. And as a bonus, I actually found font design history to be absolutely fascinating. If you love learning and creating, Skillshare places exceptional educators and resources right at your fingertips. And the first 1,000 viewers to sign up through my link in the description will get a 1-month free trial of Skillshare so that you can start exploring your creativity today. So go check out their community and help support my channel in the process. Thanks, Skillshare. Let's just pause this Sputnik-looking furnace core for a minute to talk about the Minecraft-looking part, the outer cube. I chose aluminum because it's lightweight, strong, and naturally a similar color to the stone of the furnace. Now, if this cube were true to scale, it would be a 1 cube meter, just over 3 feet. However, if it's gonna fit inside the minecart, and heck, through a doorway, it needs to be smaller. Plus, aluminum is crazy expensive right now, so I decided to work with standard sizes and make it a slightly smaller 2-foot square. But trust me, this thing is not small. I ordered 3 8-inch thick 2x4 foot sheets of aluminum and cut them down the middle to make the 6 squares necessary for the cube, and assembled them with aluminum L brackets and stainless hardware. This is all fairly straightforward, but getting the right finish was not. I wanted to work with the natural color of the material, not cover it with paint, so I decided to engrave some of the darker pixels to give it the look of the furnace without using such a large grayscale. Once they were engraved, I sanded them with an abrasive scrubber material to dull the finish, then attempted various color fill techniques. It was difficult to get enough contrast with the finely engraved lines. Then I had an idea. Did you know that they make high-temperature Sharpies? By mounting the Sharpies to a sliding stage, I was able to make a basic line drawer out of my giant CNC machine, and carefully trace the lines in permanent ink onto the aluminum. I may want to change this finish in the future, maybe with thin layers of various metals to achieve the greater color palette of the actual Minecraft furnace naturally. But leave me a comment below. Tell me how you would do it. Now, we all know that the front of the furnace has 2 openings, the bottom where the coal burns, and the top where food or materials are heated. Here's how my furnace uses them. The top is where 2 fans blow air out. This causes air to get pulled in the bottom opening. Once inside, the air is forced to pass through the heat sinks on either side of the furnace, cooling them down. Then it has to pass up to the 2nd floor, through the back corners, and then out the front. There is, however, a second air duct system back inside the inner cube. You see, coal needs a lot of airflow in order to burn efficiently. And with the 2 big fans creating suction and airflow in the outer cube, smoke could very easily get pulled out of the inner chamber and then blown out the front. So I needed to create even greater suction inside the inner cube, and I did this by putting a fan inside the exhaust pipe of the furnace. Now, it's very difficult to find fans designed for this kind of heat, so I built it myself. A motor is attached to a titanium plate underneath the exhaust elbow, and a long shaft runs up into the pipe, where it's attached to an aluminum fan blade, which I made on my CNC machine. This solution is good enough for now. It generates a lot of suction inside the chamber, and as long as the pressure inside the inner chamber is lower than the pressure inside the outer chamber, the smoke will all flow out the exhaust that runs through the top, keeping the heatsink exhaust clear and feeding the coals plenty of oxygen for optimal combustion. Now, theoretically, this whole system should work great, but reality has a way of ensuring that all creative endeavors are optimally challenging. First, there were the problems with my CNC machine. I don't know what's going on. My machine is behaving strangely, but not in a way that's consistent. I mean, I've got $700+ worth of aluminum here, and I'm not in the mood to have an unpredictable machine cutting into it. And of course, once I solved that problem, then I realized that my 2 giant used heat sinks had different mounting holes. You know when they say measure twice, what they mean is that if you have 2 different pieces, measure both of them because they're probably different. This is to basically ignore the issues that I had with the buck converters that were supposed to control my fans, or the problems I had with the thermocouples that were supposed to monitor the temperatures of the exhaust pipe and the heatsink. Now, to be fair, these kinds of issues are to be expected when taking on a massive project. I really pushed myself to design, fabricate, test, and make a video about this beast of a prototype in a pretty small window of time, so I shouldn't be too surprised. But each mistake and setback is especially painful when you're spending a lot of money on specialty materials. Thankfully, I have you guys. When you subscribe to my channel and like and share and all that good stuff, it gives me both the budget and the confidence I need to try something like this. So thank you. I literally could not do this without you. Difficulties or not, progress had to be made, which meant early testing with an electric heating element instead of coal. And that's where I discovered a few more issues. Well, we're at over 300 degrees Fahrenheit inside this chamber now. You know, why aren't we generating enough to even turn on a fan? Come on, buddy. Basically, I wasn't getting anywhere near the power output that I thought I would get. Energy output is not good. Yeah, we're up to like almost 400 degrees Fahrenheit inside that chamber. Why are you so wildly inefficient? And I'm getting like 6 volts. It's gotta be a mistake on my part. So I hopped on the phone with the manufacturer of these cells to try and figure out what I was doing wrong.
These resistance numbers like above 1 mega ohm.
I'm not using the ceramic wafers, I'm using anodized plates.
Ignore those. We think it's just some kind of capacitance. How flat is that surface?
With some fresh perspective, I was tired but determined to make things better. But gotta see it through. I decided to improve the clamp system and increase the internal thermal mass. I started by cutting strong 1/4-inch plates to ensure that the clamping pressure was flat and evenly distributed across the cells. I then attached heat sinks to increase the thermal mass and surface area inside the chamber, to pull more heat more quickly off the burning coals. The coals themselves sit inside of a special basket that slides into the chamber. The bottom of the basket is cast iron, and the top is aluminum, with steel screws creating the walls. Thankfully, I found a bunch of them for cheap at a building materials thrift store. Now, in order to access the inside of the furnace, the faceplate snaps on and off using some cabinet latches. I considered hinges, but one day this furnace may be running in the minecart, and there's very little space for a swinging door. After putting some finishing touches on the second floor of the chamber, my cameraman Quincy came over to help me with the first coal-powered test. Now this is the point where I discovered some of the issues with the thermocouples and converters, so I hastily ran the wires out the front of the chamber so that I could switch between external and internal power without the converters. We started with it open because I would need to get the coal fire going before I could close it up and begin the active cooling process. Did I mention that I've never made a coal fire before? Apparently, it's not that easy to get them burning.
I like an anthracite coal forge. Once you get past the learning curve, and that's what it is with all the forge fuels, there is a learning curve.
Thankfully, the furnace in Minecraft can burn on multiple other fuel sources, including wood and charcoal. But ultimately, I still wanted to burn anthracite coal. So we hit the store and grabbed some charcoal and fire starters. I layered these under the coal so that I could get them burning more easily, and then as they got hotter and hotter, they would eventually get the actual coal burning, and that made all the difference.
This has the weirdest effect, do you see that?
Yeah, it burns. After a bit of torching, it quickly became evident that the furnace fan was feeding plenty of oxygen to the burning fuel, sustaining combustion, even though it was currently running off of an external power supply. It's sustaining the red glow now.
Yeah.
Which is a really good sign. I took advantage of the lack of heat buildup to quickly adjust the brass fan stabilizer, since it was running a bit wonky. That's one of the fan blades. Like I said, good enough for now. That's one of the fan blades. With basic combustion happening, I wasn't expecting to see much when I did my first voltage check. We're at 8 volts? Holy cow! With it already exceeding my indoor tests, I got the heatsink fans running on the external power supply to ensure that the thermal cells would not be damaged by the excess heat buildup. Man, this thing's staying, this is nice though, feel this.
Sorry, I didn't mean that.
That's... I tried to run the fans through the inefficient buck converters, but they just couldn't muster the strength. Nope. Then I decided to just run the fans directly off the cells, and it's running itself. It's generating its own power. It's self-sustaining. Well, the coal is what's sustaining it, but it's just burning coal. These fans are going, and this fan's going, all just off the power that this is generating. And there's a short circuit somewhere, so there's definitely things that need improvement. But it's running 3 fans. That's a lot of air. That's a lot, plus this. It's hot. So it's at 8.4, but it's climbing. This was a massive victory, but just running itself isn't quite enough. For this first test, I had to run at least one external device. So I hooked up a buck converter USB module.
Yeah!
It's struggling. It's charging, but
yeah.
it's pulled our voltage down to 6. Let's give it a chance to gain a little more momentum. Let's make sure it's loaded up properly.
That is Is that burning your hands?
I was like, titanium, that'll insulate real well. Not quite as well as I would have hoped. Oh yeah, the front sliding plate was titanium too, so that it would be easier to handle and dissipate less heat into the air coming into the intake. After a little more time and tweaking, it ran my phone and the fans, though they still bogged down a fair amount. Top is getting warm. It's toasty in some spots. So I think I need to insulate the furnace so that the air moving over it is not cooling, because right now we're cooling the furnace, which we don't want to do. We want to cool just the heatsink. With no load on the cells, we were able to achieve an output of almost 18 volts at its highest. But this is only around 20% of what these cells should be able to do in an optimal environment. There are several clear things that I can do to improve the efficiency of this furnace, like insulating the core, checking the clamp flatness and pressure, tracking down possible voltage leaks and short circuits, finding more efficient converters and better temperature monitors, and optimizing thermal mass distribution. But if I do all of these, and any other tweaks that I haven't thought of yet, will it be enough to power the minecart up to furnace cart top speed? Honestly, I don't know. Worst case scenario, this outer cube can easily be repurposed to hold a different coal power plant. But I know that I've found thermoelectric power to be fascinating ever since I first learned that it's used to harness the waste heat from radioactive materials in order to power some satellites and other remote equipment. But maybe it's not worth the effort and uncertainty. Maybe your vision for the furnace cart is totally different. Please, let me know in the comments exactly what you think. Thank you for being a part of this journey and for your patience in my learning process. The best lessons in life often aren't easy. And let's just say, I've been learning a lot lately. I'll see you next time.